going to do the next section in the probability and statistics unit, which is on general probability. We're going to cover single event probability, basically the likelihood of a single one event occurring, multiple event, which can be one event occurring and another event occurring, or one event occurring or another one event occurring, and then finally what I'll call conditional probability, which I'll define in a moment. First of all, just a definition of probability. We mentioned this in our last lesson, but probability is the likelihood of an event or outcome occurring. It's measured between 0 and 1, or often done in percentages, so it's 0% to 100%. And 100% is it will definitely occur. 0% is it cannot possibly occur. Okay, so we're going to go through each one of these. I'm going to start with single event probability, the likelihood of a single event occurring. There are two types of ways of finding probability. One is experimental, and the other one is theoretical. Experimental is just done through measurement. Let me give an example of that. If you say there is a 30% chance of snow tomorrow, 30% chance of snow. First of all, that's a probability. And generally when you write probability, you write P for probability of, and then you write the event in. So I'll put P of snow. And that equals 30%. So how did I get that 30%? In no way is that mathematically calculated in a theoretical manner. It is done by observing days. So when someone says there's a 30% chance of snow, they have a database of all the days that looked like tomorrow from a weather perspective leading up to it, and said 30 out of those, say 30 out of the 100 days they observed, or 300 out of 1,000, it snowed. In other words, they didn't actually calculate it, they just collected data that showed it. Let me give you another example. If you have a football player who completes 30 out of 40 passes in a game, say, and you say, what is the probability that his next pass will be completed? You're not going to calculate that. What you're just going to do, I mean, theoretically calculate it, I don't know, based on his arm strength or something. You're actually going to take his historic completions, which is 30 out of 40, which is 75%, and say, I'm assuming the next pass is also going to have a 75% probability of being completed. Obviously that could be false, as could this be one, because you're just collecting data. There's no mathematical way of saying it's 30% other than I collected a bunch of data. And if you happen to collect the data incorrectly, or in this case, for example, he injures his arm and suddenly he can't complete 75% of his passes anymore, or he's just having a good day, you're not going to get a great prediction. However, this is actually, this method of experimental, what's called experimental probability, is the predominant way that probability is done. And that's because, as you'll see in a moment, the theoretical ones are very hard to calculate except for very simple cases. So most of probability is just done by looking at data and predicting things from it. Okay, let me give you another example of experimental probability. I hope you can read this. I have a chart here. Might be a little small, you might have to blow it up on your screen a little bit. This is the marriage status or marital status of the US population, 15 and older. And on the left here you have male, female, total. The top you have married, never married, divorced, widowed, and total by line. So there are 242 million people in total that they put in these numbers who are 15 or older in the country. By the way, there's like 330 million people in the country total. So this doesn't include the 15 and younger. Okay, so here's data just collected again. And if I picked one person randomly from this, what is the probability that the person is divorced? By the way, these are extremely common SAT-like problems. They give you these tables and ask probabilities. So what is the probability that they're divorced if I just pick someone randomly? Well, you go to the table, it says divorced. The total number of divorces is 24. And the total, in total, is 242. So the probability of me picking someone out divorced is 24 out of 242. Again, I didn't really calculate that other than just pulling a bunch of data. This is a probability pulled from a bunch of experimental or found data. Okay, so let me give another one. What is the probability that someone has never been married? So now you go down the never married category. Sorry, this probably, let's write this down. This was divorced. Then you have never married. So never married, there are a total of 74. Again, we have 242 total. So my probability of randomly picking someone and having them be never married is 74 out of 242. It also says if you're in the United States, the probability of you never being married, if you're 15 and older, is 74 out of 242, and you can convert that to a percentage if you wanted to do that 0 to 1 or 0 to 100%. And you do 74 divided by 242. And you get 30.6%. So there's a 30.6% chance that I'll be never married if I just randomly pick someone. Okay, let me give another one. What is the probability that I am male? Randomly selected in this population. Again, now you look at male, you look at the row instead. There are 118 total males. And again, out of 242 total. So that is 49% chance that I'll be male. Presumably the other percent chance is female. Again, these are all experimental. I didn't calculate anything. I just collected a bunch of data, and I assume that any random population I pull out of is going to look like this selection. And then I can get percentage of various things. Okay, so that's experimental probability. We're now going to do theoretical probability, the next part right there. Okay, the theoretical probability is mathematically calculated. In fact, let me erase some of this stuff so we have a little more room. I'll leave up the word probability. So theoretical probability is mathematically calculated. And part of that is the stuff we did last time, which is calculating the total number of outcomes, for example, as a denominator. Total number of outcomes. And in the top we had desired outcome. And as you recall, we spent a lot of time doing this with permutations, combinations, and fundamental counting principle. We're now going to put it into probability. So let me define theoretical probability. So probability, we'll write again P for probability. The probability of an event A occurring is equal to M. M desired, M will be the desired outcome, just as I wrote here, divided by the sample space of n outcomes. Just usually written by M divided by n. In order to do this probability, you have to have what are called equally likely outcomes. So an example of that would be, for example, rolling a dice. The odds, or the probability of getting a 1 is the same as getting a 2, a 3, a 4, or a 5, or a 6. They're all equally likely. So you generally do equally likely outcomes down here. I'll put that here. Equally likely outcomes. And, okay, so these are really hard to do theoretical calculations like this. They are done, but I'm going to do it with some simple examples just to give you a feel for them. And we're just going to use things like cards, dice, drawing marbles from a bag, things like that. So I'm going to start with coins, flipping a coin. So we're going to do probability of, do coin flips first. So first, if you flip one coin, what is the probability of getting a head? We did this last one as well. So the total number of outcomes are heads and tails. So there's 2 total outcomes, heads or tails. And they are equally likely. If you flip a coin, you're equally likely to get a head as a tail, in a fair coin anyway. And then on the top you have the desired outcome, which is your numerator. In this case, how many different ways could you get it? Your desired outcome is just a head, one possible outcome. So what is your chance of getting, what your probability of getting head? 1/2, which is written typically as 50%, or if you want it between 0 and 1, 0.5. Okay, so now what is the probability of getting 2 heads, say to 2 coin flips instead, and getting 2 heads? This is a little harder, and we did this last time as well. If you have 2 coins, the total number of outcomes of 2 coins is actually 4 total outcomes. It's 2 times 2 by the fundamental counting principle. And I can even write them out. They're head, 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 tail, tail, head, or tail, tail. So there's my 4 outcomes. If I want to get 2 heads, there's only one possibility. There's the head, head. There's 1. So the probability of getting 2 coins and 2 heads is in fact 1/4, or 25%, or 0.25. Okay, let's do last one. 3 coins. What is the probability of getting 3 heads? Again, 3 coins. You can use the fundamental counting principle to get the total number of outcomes. 2 times 2 times 2. So that's over 8. And what is the probability of getting heads? There's only one way to do that. It's head, head, head. So one way to do that. So that's 1/8, which is 12.5%, or 0.125. Again, this is not done through experimentation. It's just numerically understanding a coin and calculating a probability from that. That's the difference between experimental and theoretical. Okay, now we're going to do dice. Dice rolling. By the way, the reason these are simple ideas or simple ways of doing this is it's really hard. There aren't that many things that you can come up with that actually have equally likely outcomes. Okay, so let's go, let's say what are the probability of getting a 5 on a single 6-sided dice. So again, probability of a 5, put that P of 5, probability of a 5. How many ways can you get a 5? Only one, 5. How many different total outcomes do you have? Just 6. So the probability of getting a 5 is 1/6, which is 16.6 repeated percent chance. 1/6. Okay, I think that most people get that. It's pretty straightforward. Now we'll do, what is the probability of getting 2 6s on 2 rolls of the 6-sided dice? Okay, so first of all, so probability of a 6 and a 6. How many different ways, how many different outcomes can you possibly get? Well, you roll one 6-sided dice, then you roll another one. Fundamental counting theorem says you have 6, or counting principle says you have 6 times 6 total possible rolls, or 36 in total. And how can you get 2 6s? Well, the only way to get 2 6s out of all these outcomes is just to get 6 and then 6. There's only one way to do it. So the probability of getting 2 6s in a row is 1/36, a very small percentage. And I'll write that as a percentage as well. It's 2.77 repeated percent chance. Very small. Okay, now we're going to do a little trickier one with dice. What is the probability of getting a total of 7 on 2 rolls of 6-sided dice? So probability of total of 7. So again, the denominator is 36. Fundamental counting principle says this is just 6 times 6 total number of outcomes. Now the question is, how can you get a 7? You have to go through and actually manually do this. You can get a 7 through a 1 and a 6. 1 the first time, 6 the second, or a 6 and a 1, or a 3 and a 4, or a 4 and a 3, or a 2 and a 5, or a 5 and a 2. Those are the 6 out of the 36 possible rolls you could get, which would give you a total of 7. So there's 6 different ways to do that. For 6/36 is 1/6, or 16.6 repeated percent chance of rolling a 7. Okay, I'm going to have you guys do one with a dice. One last one. What is the probability of getting a 4 or a 10 in 2 rolls? Be a 4 or a 10. Okay, pause the video there. Try to get that one yourself. Okay, if you're back, Still 2 rolls, so it's still 6 total possible outcomes. How can you get a 4 or a 10? You can get a 4 through 1, 3, or 3, 1, or 2, 2. There's 3 different ways to get a 4. How many ways can you get a 10? There is 4, 6, 6, 4, and 5, 5. So there's 3 ways to get a 10 as well. So what is the probability of getting a 4 or a 10? There's 6 total possibilities. And again, it's 1/6. That's just coincidence, by the way. There's 3 1/6 there. Okay, so that's dice. Let me try one more, which is we're going to use cards now. Now, I recognize some of you are probably not familiar with a deck of cards, so I'll do a little bit of explaining of that first. So cards. So a card deck has 52 cards in it, broken into 4 suits. 2 red ones, hearts and diamonds, 2 black ones, spades and clubs. So give a couple of examples on this. Oh, and then also just a couple of terms for it that you'll need for some of the homework as well. Of the 13 cards per suit, so there's 13 each, there are 3 face cards, which are the jack, the queen, and the king. You'll need to know that. That's probably about all you need to know to actually do the problems. Okay, so let's do some problems on it. So let's start with, what is the probability of getting an ace if you just draw a random card out of the deck? So an ace, there are 4 aces, 1 per each suit. Oh, one other thing, if you don't do cards, the cards are 2 through 10, then jack, queen, king, and an ace for each suit. That's what gives you the 13 cards. So if you take an ace out, there are a total of 52 cards. So the total number of outcomes is 52. And how many aces do you have? 1 per suit, or 4. So the probability of getting an ace is 4 out of 52, which I'll give as a percentage again. That's P of, what is that? P of A, of an ace. 4 out of 52, which is 7.6, or 7.7 roughly, percent probability. Okay, so what's the probability of getting a face card? P of face. Again, there's 52 cards. How many face cards do we have? 3 face cards per suit. So 3 times 4 is 12, or 12 50-seconds, which is 0.23, or 23.1%. Okay, I'll give you a couple more to do yourselves. Tell me what is the probability of getting a red card if you randomly pull out, and what is the probability of getting a spade? So pause there so you can get those 2. Or if you're back, the probability of the red card, again there's 52 total cards. Red is half the deck, so you should know it's half. But there are 26, 2 suits of the 4, so there's 26 total cards that are red. So it's 26 over 52, or 1/2, or 50%. Probability of a spade. Spade is one of the 4 suits. So out of the 52 cards, 13 are spades, or 1/4, or 25%. Okay, we're going to come back to things like cards when we have some a little more complicated calculations to do. This is, again, just single event probability. All right, now we're going to go to, we're still going to do theoretical probability. We're now going to do multiple event probability. So this is 2 events occurring. And we are going to start, we have to actually explain a couple of theoretic terms first before doing multiple event probability. Multiple event probability we're going to do are for what are called independent events. And I'll talk about what that means in a second. And then we'll do some called with dependent ones as well, but not till after we do the independent ones. Okay, so what does independent mean? Independent means that one event is not caused or related to the other one. And dependent ones mean they are related. And I'll give you an example of what means related. So again, independent means one event is not caused or related to the other event. So for example, if I had a probability, for example, of is it going to snow tomorrow, and it was 30% chance of snow, and then I said, what is the probability that it'll be less than 40 degrees? And I said that's, I don't know, 40%. So these events are heavily dependent on each other. If it's going to be, it's very unlikely to snow if it's bigger than 40 degrees. The snow depends on the temperature to a degree. So those are dependent on each other, and therefore it's actually really hard to calculate probabilities of, for example, it being snowing and less than 40, for example. And some of the things I'll talk about here won't actually apply. Let me talk about things, let me give you an independent event. Probability of getting ahead when you flip a coin, and when you flip a coin, and the probability of separately getting a 5 when you pull a card out of a deck. So this event has nothing to do with that event. They're not even in the same, I mean, this is coins, that's cards. It's not like these where snow depends on the temperature. Okay, so if the events, we're going to largely focus this in here on independent events for the moment. If you have two events occurring and they are independent, the probability of two events, so you have a probability of one event occurring A and another probability of another event occurring B, and you say what is the probability of both of them occurring, B and B, A and B, it is simply the multiple of the two. Probability of A occurring times probability of B occurring. Again, as long as they are independent from each other. So let me give some examples of that. I'm going to use the things like coins and cards and things like that just to make it simpler. So let's start with dice. So I'll give you an example of this. What is the probability of getting a 2 the first time you roll a dice? Yeah, 2 first time. And a 3 the second time. So you're going to roll a dice. You want to get a 2 the first time, a 3 the second time. Okay, so what you do, as long as these are independent from each other, which they are, if you roll a 2 the first time, it's not any harder or easier to get 3 the second time. It's the same. In other words, this one doesn't affect that one. So what is the probability of getting a 2 the first time? It is 1 out of 6, if it's a 6-sided die. What is the probability of getting a 2? So it's probably a 2. What is the probability of getting a 3 the second time you roll? That is also 1 out of 6. So what is the probability of getting a 2 and then a 3? If you just roll it randomly, probability of 2 and 3, it is 1/6 times 1/6. Probability of 2 times probability of 3. Let's write that first. Times 1/6, or 1/36. Okay, let's try another one. What is the probability of getting an even number if you're rolling a dice the first time, and then a number greater than 2? So a 3, 4, 5, 6. Okay, so what is the probability of both those occurring? It is simply the probability of multiplied together. So the probability of an even and then a greater than 2 is simply the probability of even times the probability of greater than 2. And let's put numbers in. The probability of a number getting even when you roll a dice is 2, 4, or 6. 3 possibilities out of 6 total outcomes. Probability of getting a bigger than a 2 is 3, 4, 5, 6, which is 4 possibilities out of 6. So the probability of getting an even number and then secondarily getting a 3, 4, 5, 6 is 3, 6 times 4, 6, or 12, 36, or 1/3 total. Okay, I'll have you guys do one now, again with dice. Okay, here we go. So what is the probability of getting an odd number? That's not a 0, that's odd. the first time, and then a number less than 3 the second time. Okay, pause the video there and calculate that. All right, so the probability of an odd first is again 6 total. Odd is 1, 3, 5, so that's 3. Probability of less than 3, you can get a 1 or a 2. Only 2 ways to do that. 2 times 6. This just says if you want both, probability of odd and less than 3, then you just multiply them out. 3 times 2 is 6, over 6 times 6 is 36, or 1/6. Okay, let's do a card example. So what is the probability of picking an ace? And then from a new deck, I'll talk about why that's important in a moment. The next time, first, putting the ace back, and then second time, the probability of getting a 4, second, and then a probability of getting a, let's say, a face card, third. Now I didn't do 3 events this time, but all you have to do is multiply these 3 probabilities together to get the probability of that occurring, which is going to be very small, by the way. Okay, so let's do that. Probability of an ace is 4 aces out of 52 total. Probability of 4, there's 4 fours, 4 out of 52 total. Probability of a face card, remember there are 3 per 52, or 3 per suit, so there are 12 total out of 52. And if I want to know the odds of this occurring, all of this occurring, in other words, getting an ace, then getting a 4, then getting a face card, it is simply 4 times 4 times 12. 4 times 4 times 12, which is 192, over 52 times 52 times 52, 146.08. So 192 divided by 146.08 is 0.1%. Very, very low odds. Now, why did I have to say you have to put the card back? Because if you took this out, if you said, what did you do this, and then you leave the card out, it's not actually this. It would be 4 50-seconds. The next time around, you've actually only got 51 cards to choose from. So it's 451, and now you've only got 50 because you're taking a card out every time. And the face card was 12. So that's a different number. So this just assumes you put the card back every time. If you don't put the card back, then you've got 1 less card every time. Still the same method though. Multiply the probabilities together. Okay. So now we can go back, by the way, to our original example, which was flipping a coin. And say, what is the probability of 3 heads if you flip 3 coins? Well, the probability of getting that is simply 1/2 the probability of getting 1 head, and so it's times the probability of getting another one, times the probability of getting another one, which is 1/8, which is the same thing we got when we just added up all the ways you could get 3 coins, or the outcomes of 3 coins, 2 times 2 times 2. All right, that's an and, what's called an and probability, and I'm going to leave that up there. It's, again, it is very important that those events be independent from each other to be able to do this. In other words, this can't affect this one, and this one can't affect this one. If they can't affect each other, there's a totally different probability calculation. Okay, next what we're going to do is what is called an OR probability. OR B. And that one is simply the probability of one plus the probability of the other one, minus the probability of both of them occurring. So this, for example, it would say, what is the probability, if you flip a coin, let me give an example of this. What is the probability, if you flip a coin, of getting a head or a tail? I think everyone would say, well, as they flip one coin, what are the odds you're going to get a head or tail? 100%, unless it can, land on its side. This just shows you how you calculate that. Probability of A or B is the probability of a head, so probability of head or tail, is the probability of the head plus the probability of the tail minus the probability of the head and the tail. Now you can't both get a head and a tail, so this is actually 0. You can't, unless you have a really strange coin that can simultaneously get a head or a tail. That's 0. So it's just the sum of these two. Probability of the head is a half. Probability of the tail is a half. Probability of both of them together is 1 or 100%. You are going to get a head or a tail if you flip a coin. All right, so there's my next formula. This part here will be 0 if events are what are called mutually exclusive. Means they can't both happen. So write that down as well. Can't both happen at the same time. An example again would be if this is probably A is like the probability of rain, probability of sun, or probability of rain, probability of no rain would be a better example. What is the probability of rain and no rain? 0. So a lot of the calculations you'll just be adding them. Okay, before we do a couple more examples on this, just a summary. So if you're doing independent events, multiple events, more than one event occurring, and you want to find out what the probability of two things both occurring, A and B, you just multiply them together. If you want a probability of either of them occurring, you just add them. Then you have to make sure you subtract out the probability of A and B also occurring, which you could do this way. But that is often 0. Okay, so let's give examples. We'll do it with cards again. So what is the probability that you are dealt a random deck of 52 cards? You are dealt a 2 or a 3. Okay, so the probability of 2 or 3. So all you do is the probability of getting a 2, which is 4 out of 52. There are 4 2s. You add that to the probability of getting a 3, which is 3, is 4, again, 4 3s out of 52, minus the probability of getting a 3 and a 2 if you pull a card out, which is 0. You can't pull one card out, you can't both get a 3 and a 2. So minus 0, or 8 50-seconds. There you go, just straight add them. Let's try another one. Probability of being dealt a 7 or a red card. Okay, probability of a 7, there are 4 of those again, out of 52. Probability of a red card, there are 26 red cards out of 52. Now this time, you can both be a 7 and a red card. For example, you can have a 7 of diamonds or a 7 of hearts. So you have to subtract the probability of that. So 7 diamonds, 7 hearts are my 2 possibilities out of 52. So in this case, this is the probability of a 7 and a red card. Whereas this is the probability of a 7, and this is the probability of a red. So you have 4 plus 26 is 30, minus 2 is 28 50-seconds. That's the probability of getting a 7 or a red card if you just pull a card out of the deck. Okay, let's try another one. Probability of a red 7 or a black 8. Okay, why don't you pause it there, try to do that yourself. Okay, if you're back, again an or, so you're just adding them. What is the probability of a red 7? There are 2 red 7s out of 52 cards. And what is the probability of getting a black 8? There are 2 black 8s, the 8 of spades and the 8 of clubs out of 52 cards. What is the probability of a red 7 and a black 8? You can't both get those simultaneously. It's not like here where you can get a 7, red 7. You can't get a black 8 and a red 7 if you're pulling one card out. So this is just 0 or 4 50-seconds total. Okay, the last thing we're going to, actually let me give you one more example before we go there. Just something that isn't so theoretical, it's just cards and such. The reason you use these is just they're easy to calculate. Okay, I'm going to give one more example. Let's say you're at high school and a student can take one foreign language at a time. And let's say you have 37% of the kids are taking Spanish and 15% are taking French. So what is the probability that you're taking Spanish or French? Well, the or again would just say it's the probability of Spanish plus the probability of French minus the probability of Spanish and French. Probability of Spanish is 37%. Probability of French is 15%. Probability of Spanish and French is 0. And the only reason it's 0 is because you can only take one foreign language. If you could take two, you'd need to know this number to be able to get the actual percentage of people taking Spanish or French, because there'd be overlap. So this would be 37 plus 15, which is 52% total that they are taking Spanish or French. Okay, the last thing we're going to do is the dependent or related probabilities. So again, these are independent events. We're now going to do dependent events, where one actually is related to the other one. So the way you write that, so this is dependent, is probability B straight line down A, which means probability of event E, event probability of event B given event A has occurred. This is called conditional probability. So again, probability of some event occurring given that someone else has already happened. So an example of that would be, what is the probability of it snowing today given that it snowed yesterday? The fact that it snowed yesterday will affect whether it snows today, might be a higher probability, and therefore they're not independent of each other. If it snows today, it's more likely to snow tomorrow than if it didn't snow today. So one event is dependent on the other. Okay, I'm going to give you a couple examples off of tables. I'm going to go back to the original table I had. So I make sure you have all this written down, by the way. That's all the formulas we're going to have. So I'm going to go back to the original table we had. And we use that, this is experimental probability, but I'm now going to use, I'm going to do a bunch of conditional probabilities. So I'm going to say, what is the probability of being married given that you are male? Okay, so what you do on this, and again, these are very common SAT problems, well, they're not usually written like this. What you say is, you are given that you're male, so you're dealing with this row here, male, 65, 40, 10, 3, and 118. Just this line item. So if you're male, what is the probability that you're married? So the total married is 65. The total is not 242, it's 118, because it's given that you're male. So 65 out of 118. So again, that's conditional probability. We're assuming you're male, that's your first event. Then what is the probability that you're married? So 65 out of 118, not 65 out of 242. Okay, let me give you another example. Probability of male given you're divorced. So this column goes the other direction. So now we're assuming divorced, so we're only dealing with this column. Divorced, 10, 14, and 24. You can't read that. So the denominator is divorced, 24 total. And then what are the odds you're male if you're divorced? 10 out of 24, which as a percentage is 42% chance. Okay, so that's conditional probability. Let me have you try one. What is the probability given you are widowed that you are male? Okay, pause it, try to get that. right, so you're given that you're widowed, so you're in this column here, widowed 3, 11, 14. So the total is 14. What is the probability you're male? 3/14, or 21%. Okay, I'm going to do one more with the table. Let me erase all this here. I'm going to leave this up because this is a good summary of the whole probability. Okay, so here's another table. Maybe a little easier to read as well, as it's much bigger. So this is gender of students in college by 2-year, 4-year, and graduate school. By the way, one thing you'll notice in here, which is very factually correct, this is real data. Well, I think it's from like 10 years ago. There are way more women in upper level education than there are men by a long ways at all levels. 2-year colleges, 4-year colleges, and graduate schools. Okay, so anyway, there's my table. So we're going to do some of these probability events again. Conditional probability. What is the probability if you are in graduate school that you are female? So again, if you're talking about graduate school, over here, you're talking about just this row only. Graduate school, 1349, 1954. So your denominator of the total number of graduate school, which I don't actually have totaled here, is just 1349 plus 1954. That's your total. And then what's the probability of, if you're in that row that you're female, it's 1954 over the total. So 1954 divided by 1349 plus 1954, or 59%. Again, conditional probability, you're assuming this has occurred, and this is the event you're actually checking the probability, given that that's occurred. Okay, we'll try one more for you guys to do. So what is the probability that, given that you're male, that you are in a 2-year college? Okay, try that yourself. All right, so in this case, the denominator is male. You're just in this column. You're automatically assuming it's male, so you're not dealing with this part of the data at all. So the denominator is 1866 plus 4324 plus 1349, or 7,539. This doesn't have nice total columns like the other one, but you just have to add up that. And then, given that, what is the probability you're at a 2-year college? It's 1866. There we go. And I'll get that number for you as well, just by dividing it out. 25%, 24.75%. All right, that's it. Let me do a brief summary, and then I'll put out the homework. Okay, so we were talking about probability, which is the likelihood that an event occurs. It's calculated between 0 and 1, or more typically 0 to 100%. We talked about 2 different ways of doing probability. One was experimental, which is how it's mostly done. Experimental. And the other one was theoretical, which is calculated mathematically. Okay. The theoretical calculation, we had 3 different calculations we did. 2 for events that are independent, events that are not related to each other, and 1 for when they are related to each other. Independent calculation, or independent probability, is we have an and. What is the probability of 2 events both occurring? In that case, you multiply them together, the individual probabilities. What is the probability of one or the other occurring? You add them and subtract the probability of both of them occurring, if that is possible. And then finally, dependent probability is where one event depends on another one. The effect A occurring, effect B, and it's written as probably B bar A, which means the probability of event B occurring given that event A has already occurred. And these you can do, again, you can do them theoretically if you have these probabilities, but most of these times these are done through experimental calculations or data, like we did in our tables. All right, that's it. I know that's a lot of new material for a lot of you. The homework is homework number 21, which is called probability. And that's it. Thanks.